folks, welcome to section 7.4. Here we're going to learn about something called partial fractions. We're going to learn the algebra behind partial fractions. It's really when you separate a rational expression into different fractions, and I'll talk about it obviously a little bit later, but we'll do the algebra side of things for this concept of partial fractions, and then you will revisit this again when you get into calculus, specifically integration techniques. You're going to use it there. So this is definitely going to come back around in calculus. And what I'm going to teach you in this section is I'm going to teach you how to decompose fractions, right? A rational expression. Decompose a fraction that has what we call non-repeated linear factors, meaning I have a fraction where my denominator has some, and I say my denominator, q of x, has something like x plus 3, x minus 4. Those are linear factors. And they're called non-repeated in that the power on each of these binomial factors, right, these linear factors, is 1. So we would call those non-repeated linear factors. And I'll just leave the 1 here for fun. And then we'll also look at fractions, and we'll decompose those fractions when you have repeated linear factors. So maybe you have something like x minus 4 again, but x plus 3 squared. We would call this a repeated linear factor. Repeated because the exponent is something other than 1. Linear because the power on my variable term is 1. Right? So this is a linear factor, but it's repeated. This is a linear factor. It's not repeated because the exponent on that binomial is 1. Okay? And it doesn't have to have an exponent of 2 to be repeated. So if I had x minus 4 cubed, this now would be a repeated linear factor, and this would as well be a repeated linear factor. Then you can have non-repeated irreducible quadratic factors. So let's talk about that. So sometimes your denominator, q of x, might have something like, and I'll put it here, like x squared plus 1. All right, so let's say my denominator had an x squared plus 1. Well, that is a sum of squares, right? Sum of squares is irreducible. It's prime. I can't break that down. And if this exponent is raised to the first power, it's a non-repeated irreducible quadratic factor. Again, quadratic factor because the x variable here is squared. Non-repeated because that exponent is 1. So we've got a couple of exponents that we're balancing here. All right, and then we're also going to do repeated irreducible quadratic factors. So that might be something like x squared plus 1 cubed, right? So again, quadratic factor because this is an x squared term, repeated because this is an exponent. This is an exponent, other than 1. And if you want to think about, well, what's a reducible quadratic factor, right? If I had something like x squared minus 1 on my denominator, I could break that down into non-repeated linear factors because that would be a difference of squares. All right, so sometimes you'll run into quadratic factors that are prime, so we call those irreducible, right? And sometimes those irreducible quadratic factors will also be repeated. All right, so let's just kind of review up adding some fractions. Let's talk about adding some fractions. I'm going to give you what I would call 2 partial fractions here, and we're going to simplify. We're going to add the following 2 fractions. So let me scooch this up, and then let's just take a look or review up for a bit how we add fractions. And anytime you want to add fractions, you're going to need an LCD. And this LCD concept is going to come into play in this example, in example 1, and then also when we start looking at partial fractions. So if I look at these 2 fractions, I want to add them, I have to have common denominators. So my least common denominator in this case will be combining this first fraction's denominator and this second fraction's denominator. So I'll take x minus 3, x plus 2. All right, and I'll keep that in mind as my LCD. And so what I'm going to do in the process for adding fractions is I'm going to multiply this first fraction by 1 and this second fraction by 1. And when you multiply anything by 1, you don't change its value because 1 is the multiplicative identity, right? If I took 7 and I multiplied it by 1, I still get 7 back out, right? If I take x and I multiply it by 1, I still get x back out. So if I take 2 over x minus 3 and I multiply it by 1, I'm still going to get 2 over x minus 3. But what we're going to do is we're going to multiply this fraction by its unique version of 1, a special version of 1, and this fraction by a special version of 1. And here's how you decide. So you're going to take 2 over x minus 3, and I want to multiply it by a fraction. right? So something like 7 over 7, right? That would be 1. I'm not going to pick 7 over 7, but I want you to see if you had 7 over 7, this is equivalent to 1. And anytime you multiply by 1, you don't change the expression. All right, so what we wind up choosing is we look at this denominator and we look at our least common denominator. And we can see from this denominator to my LCD, I'm missing an x plus 2. So I'm going to multiply this by x plus 2 over x plus 2. Again, I'm multiplying by 1, so I didn't actually change the expression. And just so I can continue on with the problem, I'm going to erase my little scratch work here. If I take a look at that second fraction, that negative 1 over x plus 2, which I'm just going to write it with the minus sign. So I have 1 over x plus 2. I'm going to multiply this fraction by 1. It's going to be a different looking fraction of 1. So if I look at this denominator to my LCD, I'm missing the x minus 3. So I'm going to multiply this by x minus 3 over x minus 3. And keep in mind, all of these binomials are protected with parentheses. All right, so if I simplify this a little bit, with this first fraction, I have 2 times x plus 2. With my denominator, I have x minus 3x plus 2. With my second fraction, my numerator is x minus 3. And my denominator, I'm actually going to write it in the same order, x minus 3x plus 2, just so you can see that these are now common denominators. Right? And x plus 2, x minus 3 is the same as x minus 3x plus 2. It doesn't matter what order you multiply in. We call that commutative, right? And I'll just do a little scratch work, right? 3 times 4 is the same as 4 times 3. It doesn't matter what order you write them in. Okay, I'm going to erase my scratch work again. All right, so now that I have common denominators, I'm going to subtract these numerators, right? You keep the denominator, subtract the numerator, but be careful, right? This numerator is a binomial, so there's a set of parentheses protecting it. So I'm going to have 2 times x plus 2 minus an x minus 3 all over x minus 3, x plus 2. Right, and then I'm just going to go ahead and start simplifying my numerator. And as you can see, I'm kind of running out of space. I'm going to scooch this up a little just so that we can all see the rest of my work. All right, so let me go ahead and continue with this. So I'll keep my denominator of x minus 3, x plus 2. Let's see what we get here when I distribute. 2 times x, 2x. 2 times 2 is 4. Negative 1 times x minus x. Negative 1 times negative 3 plus 3. All right, and then it's on me to go ahead and simplify my numerator by collecting like terms. So I can see an x and a minus x. I see a 4 and a 3. Right, so I'm going to add the linear terms together, add the constants together. All right, 2x minus x is x. 4 plus 3 is 7. And I keep that denominator of x minus 3, x plus 2. All right. And the most you could do if you wanted to, and I'm not saying you need to do this, but the most I could do at this point was FOIL that denominator. And if I FOILed this denominator, first would give me x squared, outer positive 2x, inner negative 3x. So when I add those together, it's just minus x. And negative 3 times positive 2 is negative 6. So these would be end game answers. And I want you to see where you started, right? We started with 2 separate fractions. We added them together and got 1 fraction, all right? And so that's typically where you start in an algebra class. And what partial fractions does is it says, what if I give you this expression? What if I started you with x plus 7 over x squared minus x minus 6? Could you get backwards to these 2 separate fractions? Like I parted out the fractions, all right? So I wanna break those fractions apart, and that process is called partial fraction decomposition. So that's what we're gonna look into in section 7.4. So I'm gonna say, what if I give you this simplified sum that we just found, and I ask you to decompose the fractions, to move backwards to get me a fraction with that denominator having that factor of just x minus 3, and a second fraction where the denominator is the other factor of x minus 2. And that's what we're going to call partial fraction decomposition. All right, thanks so much. Bye.